I'm going to demonstrate language communication with autonomous systems, which is an architecture and a system that's been under development for many years now at the International Computer Sciences Institute in Berkeley. The system has the ability to do natural language understanding in a limited domain, in this case a block world, and then apply what it has understood from incoming requests to manipulating some back-end environment, in this case a simulated robot. There are a lot of aspects to the system, and today we're just going to focus on interacting with the system in a natural way while there are ongoing actions. So we'll ask the robot to move to the green box, and later on when we go over the architecture, we'll understand that underneath this there is a schematic representation of motion that's parameterized in a couple different ways. Among other things, the system understands different verbs in a natural way, treats different motion verbs as defining a different speed for the motion. So we can move at some sort of ordinary pace, or we can dash, or we can amble, meaning we're just going to wander over back to the green box. And in the middle of ambling, we can stop what we're doing. So that's the beginnings of showing that the system can be responsive while some action is ongoing. Let's do this. So we'll continue moving, but then we'll change our minds and say, let's go to the blue box after all. So that in a nutshell is what I wanted to demonstrate. Now let's talk about what's going on under the covers. This is the architecture at a very high level of the language communication with autonomous systems. I won't go into all of its detail, but draw your attention to the left side of the diagram, which we can call the language side, and the right side of the diagram, which we can call the action side. And for purposes of today's demonstration, the area where new things have been introduced is the orange box, the Xnet's box. And where it fits in the picture here is that we have some incoming text, an utterance, robot 1, stop moving. And first off, it's parsed to the extent that it's possible by the language side, but every sentence is underspecified with relation to the world in which it occurs. There's always a larger context, so we need some understanding of the world in order to understand the real meaning of the sentence. So there's also a representation of the world, and the parsed sentence is transformed into what we call an action specification and passed off to a problem solver, which maintains its model of the situation, where the boxes are, where the robot is, what it's doing, and makes use of this new representation, an Xnet, to control the API to the simulated robot, which is a software package called Morse. So let's understand what Xnets are in a little more detail. Xnets are an extension to Petri-nets. Petri-nets are a formalism that's been around for some time now to help represent distributed concurrent processing. The state of the Petri-net is defined by the places in the Petri-net, which are the circles, which can be empty as they are here, or can be marked with a token. The transitions between places are the rectangles, and they're connected with arcs, which govern the flow of control. And the numbers above each arc, which in this case are always 1, indicate the number of tokens that have to be present in order for the arc to fire. So let's get into a little more detail here. This gray portion of the Xnet indicates a standard structure, a standard semantics for events and actions that we think is applicable very widely, and suggests that we've got initially an enabled state, which says that we're ready to do the action, subject to some prerequisites which happen in the prepare transition, at which point we're fully ready to start, and we enter some ongoing phase which could last for some period of time. Then we're going to finish and be done. We can handle interrupts or exceptional conditions with the places and transitions up above. We could suspend the action, and it could be suspended. Then we can resume a suspended action, in which case it'll return to ongoing. Or we could restart an action, which requires us both to suspend it, stop what we're doing, and then start over again and go back down through the ready loop. So we'll look at that in a minute. But so these are our standard semantics. Any Xnet will have those. At bottom, in the unshaded portion, are the places and transitions necessary to represent the specifics of the task. In this case, we're moving in 2 dimensions, and this is a very simple representation of that motion. We're going to be moving, then we're going to pass through the move transition, we'll be moved, and then we might wait a bit and move some more. Waiting captures the notion that we don't want to loop at infinitely high pace. We want to wait to match up with the slower speed of the external world where the motion's actually happening. And finally, we're going to arrive where we want to be. There could be a much more detailed model of this motion, but we're really guided by the demands of the API and the task as to how granular we want to get. Okay, so let's say we were enabled. We would then fire the prepare transition because it has only one inbound arc, and that arc was populated with a token, and then we populate the outbound ready place. That in turn feeds the start transition, which has 2 output places, the moving and ongoing place. The ongoing place is going to stay that way through the life of the action, and then we would loop around the moving and moved places until we finally arrive. Now all 3 of the inbound arcs to the finish transition are populated, ongoing, moved, and arrived, and so we're done. So that's the normal flow. Supposing we were in the midst of a motion and we said, Robot 1, stop moving. This is the other way in which actions are parameterized in this system, and that's due to the structure of the Xnet itself. We have 2 different statements. We had 1, Robot 1 moved to the green box, or ambled to the green box, and in the midst of that we said Robot 1 stop moving. Those are 2 very different statements with very different syntax and meaning, but we can represent them in an economical way with this one Xnet and distinguish between them just by adding marking to a single place, the suspend place. So the system will mark the suspend place and will transition to the suspended state. Then if later we say Robot 1 continue moving, all we do is mark the resume place, and then the 2 inputs to the resume T transition will be populated and will return to ongoing. So that handles those simple types of interrupts. More complicated case is where we're in some ongoing move. We were ambling to the green box, and then we said, robot 1, move to the blue box. And that requires us to go through two sets of transitions. First, we want to suspend what we were doing, but we also want to restart it. So we populate both the suspend and restart places. We go first to suspended, and now the prerequisites are met for the restart T transition, and we go back to ready, and finally back through the start transition. And now we note back in our normal ongoing moving sort of state, but we have two tokens placed in the moving place. Is that important? Depends entirely on the application. In this application, a lot of the mechanics of the motion of the robot are handled by Morse, and they don't have to be calculated directly here in the Xnet. So this is a simple enough representation and will work. But it introduces our final topic, which is how do we interface between an Xnet and some other system. This is an area where we've contributed code to an open source Petri-net editing and debugging environment called Pipe to enable it to talk to external systems. The dotted blue boxes are a type of transition we call an external transition, which enables us, in addition to processing the tokens as we saw earlier, will also fire some external logic. And in this particular implementation, all of 4 of the external transitions that are represented here, the restart T, resume T, suspend T, and move transitions, all make use of a shared data structure called a Morse channel to communicate back and forth to Morse. For example, speed, the speed that's desired and the location are communicated through the Morse channel. And each of these transitions just says what we want Morse to do. We want it to move, we want it to stop, we want it to keep going. And this is a simple way to communicate back and forth. The other pair of external interface mechanisms are places that are marked or red, input or output places, to the external system. So these are ways for the external system to control the logic of the Xnet. Places marked by the external system include places like enabled, restart, suspend, and arrived. The first 3 are part of the standard semantics. That's how you tell the Xnet, hey, we're ready to go, or hey, stop what you're doing, or restart what you're doing. These are essentially commands or interrupts into the Xnet. The arrived place is specific to our application here and is the way that Morse tells us that we're at our destination. The places that are read by the external system are there as part of the standard semantics so that the external system can understand where we are in things and then govern its action accordingly. We could be ready, we could be ongoing, we could be done, we could be suspended. Ongoing is a state in which we normally expect to find ourselves most of the time, and in that state it might make sense to request that it be suspended. So this is the other portion of the control mechanism that the external system can use. And so that's the implementation of Xnets into the language communication with autonomous systems. Let me close by giving credit to a whole group of people over many years who have been building this architecture. That's the foundation on which we give today's demo. I hope that was interesting. Thanks for listening.